Is so as to enlighten you with the very basic ideas how to solve new JE problem in a known situation. So here we go with the problem. Of course, this problem can be made more tricky by taking away the parabola equations from it, which justification will be given soon. So here we go with a newly created problem by me. Consider a parabola and a family of lines as follows. So we have y square equals 4x as a parabola, and family of lines ms and l minus 2 intersects at point P. So these two lines intersect at the point P. Lines L3 and L minus 3 intersects lines L2 and L minus 2 at T1 S1 and T2 S2 respectively. Let S be the focus of given parabola. Then we have to answer the following based on the above information. And there is quite a huge number of problems which is basically related to the properties of parabola in a very beautiful way. So before we go further, you read the question again, and let's, as obvious in any coordinate geometry question, the first thought process should be no thought process. In the sense, like you should straight away understand the problem and try to put that information in a neat and clean diagram. So let's start with a diagram forming of this. So basically we have a fixed parabola, and then we have this family of lines. Now the beauty of this family of lines we have to harness, because maybe has they given this some arbitrary lines or are they spatials? So m square x minus my plus 1, the neat way of will be to keep this in y equal to mx plus c. So if we'll keep y equals m square x plus 1 by m, we are getting. Of course, we can divide by m provided m is not 0, which is clearly the case, because if you keep m equals 0, we'll get 1 equals 0, which is ambiguous. So this line cannot have slope equals 0. That itself is a hint, because in parabola we can't have any line having slope equal to 0. So maybe this line has some parabola connection. In the very next step, you can clearly see the parabola connection, because y equal to mx plus 1 by m we are getting. And does it remind you of the tangent equation in slope form to parabola? Oh yes, because parabola equation will be y equal to mx plus a by m is going to be the tangent equation for a general parabola. Here a equals 1, and hence the first crucial observation was the given family of lines is nothing but tangent to the parabola for different values of m. So we have y square equals 4x. You give m equals 1, we'll have a tangent. Give m equals 2, we have another tangent. Give m equals 3, we have got another tangent, and so on and so forth. M equals maybe minus 3, you give m equals minus 2, you give me m equals minus 1.0201426. So all these family of lines has a special property is they are enveloping a parabola, or they are tangent to this parabola for different slope. Clearly, when m is tending to infinity, you can see it will be y by m equal to x, because when m is tending to infinity, this term will almost die, and m tends to infinity will give x equal to 0, which is the y-axis, which is fundamentally the vertical tangent. Now, once we have filled the problem, let's move ahead. And let's fetch a diagram. And clearly the diagram is shown here. So we have a parabola y square equals 4x, and I have written S as the focus of the parabola. We draw two tangents, line having slope, so this is L of 2. As you can clearly see, as you move along the parabola, the slope of tangent line will increase, because here it has to be like going to infinity. Then again it will try to decrease, so all of a sudden minus infinity, and its magnitude it will decrease. It will go to maybe minus 2, and then further minus 1, 0, and so forth, so on. So that is a trend. So if you have this is L2, clearly the other line by symmetricity is going to be L minus 2. Now these two lines intersect at point P according to the question. We have another line having slope 3. So clearly we can see this line will be having slope 3, because it's making more angle with respect to L2. So it's better to draw diagram at least in a basic conceptual sense. We have this line which is completely kind of reflection by symmetricity, and it's having slope minus 3. So in this question, some symmetricity advantage is already imposed on the problem, because the point P will definitely lie on the x-axis, and so is the point of intersection of line L3 and L minus 3, because their slope is negative of each other. So if one guy is making an angle theta with the x-axis, the other guy is making minus theta. Hence, if one slope is tan theta, other is tan minus theta, which is -1. So there is no compulsion to take the symmetricity when we could have started the problem without symmetricity. But it's always wise to look upon these intricate details and these micro details in JEE problems. So that makes problem a little bit more cool, or at least more crisp and simple in its construction. Anyway, so now we are defining T1 in S1 as a point of intersection of L3 with those two lines, and we have T2 S2 as point of intersection of the line L minus 3 with those two lines given, which is L2 and L minus 2. So this is the complete diagram and the setup of the problem. Now let's try to head on the question. So as you can clearly see, before you blindly see the options, try to make sense out of the options, because many times option is going to give you hint of how to approach for the problems. So the first question is talking about ST1 by ST2 and SS2 by SS1. Even the second question is about some lengths. Third question is ratio of areas of two triangles. Fourth question is orthocenter. H denotes orthocenter. Fifth is again ratio of length. Sixth is product of length, and seventh is about length, and all this. So basically one very blind way of problem solving will be if I can find point P, T1, T2, S1, S2, and focus is already known, which is 1, 0. Once you know all these points, you can find all the length, and straight away you know, like, you can answer the question. But that is going to be extremely pathetic and traumatic experience of doing so. At least finding point P is not that traumatic in the sense, because of the symmetricity, these two tangents will intersect on the x-axis. So although some points finding is fine, still, like, it's better to escape this calculations of point finding. So what I'm going to use is the very fundamental property of parabola, which will solve most part of the problem. One of the property of parabola goes like this. As we already know, the image of focus on any tangent will lie on the directrix of parabola. So let's say if you have parabola S, so let's recapitulate some of the property. If I take image of focus in any random tangent, so the locus of image of focus on any tangent will lie on directrix. The second property, as all of you could recall, the foot of perpendicular. The foot of perpendicular will lie on tangent at vertex. It directly follows from this property, because you can simply drop a perpendicular from focus to directrix, and this line is vertex. Now we know, since these two guys are equals, according to midpoint theorem, let's say B and that point F, BF must be parallel to S dash, and let's call this is B dash. And not only this, VF will also be half of S dash and B dash from Thales theorem or midpoint theorem. So that shows these two lines are parallel. Now there is a line passing through vertex and parallel to directrix, and that's nothing but tangent at vertex. So that proves, like, the foot of perpendicular is definitely lying on the tangent at vertex. You can also prove the image of focus will be on directrix from other perspective. So from just definition of parabola. So let's say if I connect S to the point P where tangent is drawn, and if I drop perpendicular, that I'm leaving up to you, but you can see these two guys will be equal. And from reflection property of parabola, if a line parallel to axis, like, it will reflect a line passing through the focus will go parallel to the axis. So that simply shows, like, these two triangles are congruent or mirror image of each other, because these two angles are equal because of reflection property. Hence the image S must lie exactly at the same distance as PS, and PS dash must be on the directrix. So by this I have proved both property very logically. One of the remarkable property of the parabola, which is not so obvious from the basic geometry, is circumcenter of the point. So let's say if you have got two tangents drawn from any random point P, meeting it at, let's say, T1. So let's say we have tangents drawn from an external point P which meets parabola at some point A and B. We have got other tangent at some point C. Let's call the median at some point T and S. So now clearly we have a triangle formed by these tangents at any 3 points on the parabola. They are completely random. So this triangle will have some circumcircle. So there will be unique circle passing through 3 non-concurrent point, non-collinear point actually. And very surprisingly, the result tells like this circumcircle, independent of the location of these 3 tangents, independent of the orientation of these 3 tangents to parabola, they will always pass through the focus of parabola. So I'll give you a pure geometric proof of it right now. And the other color is the orthocenter of this. So if you'll roughly draw altitudes from the opposite side. So we have orthocenter somewhere here. So this orthocenter very surprisingly will lie on a line which is called directrix. So we have 2 remarkable property. The circumcircle formed by any 3 tangents will pass through the focus, and the orthocenter will lie on directrix. Let me prove this property, and of course you must have proved it from pure coordinate geometry approach. A pure geometrical approach is fundamentally based on a very beautiful and a smart concept of Simpson line. And what is Simpson line? I'll not go in proving the Simpson line concept, so you can just refer to other YouTube lectures or some PDF. If time permits, I'll do it in some other lectures. But basically, let me tell you what actually Simpson lines is there in a layman language. So let's say if you have a circle, any random circle, and you take up any 3 random points on the circle and join them. Now, if we have any random point P on the circle, let's drop perpendicular from P to the 3 sides. Let's call this as F1, perpendicular to side AB, extended maybe, let's call this F2, and if I drop perpendicular to side BC, let's call this F3. Then very surprisingly, it can be proved that these 3 points foot of perpendicular are always collinear. And this line which contains this 3 foot of perpendicular is known as Simpson line. So what is Simpson line? Given a random circle and a random inscribed triangle in it, you take another point on the circle, on the circumcircle. If you draw foot of perpendicular on the sides of the triangle, they will be collinear. And that will be contained in a line and given by a name of very famous mathematician, philosopher called Simpson. So Simpson line. Now how we are going to use this property for parabola? You see, very surprisingly, for the parabola, Simpson line is tangent at vertex because it's a converse of this theorem. So if we have some random point, let's say P in the universe, in the 2D universe, from where the foot of perpendicular drawn is collinear, then definitely that P must lie on the circumcircle of the triangle formed by ABC. That is the consequence of converse of Simpson line. And that's fundamentally we can capture in this. So I'm giving you a pure geometrical approach of feeling why the circumcircle must pass through the focus of the triangle formed by tangents. Okay, so it's a new approach of understanding this. So from the focus, if we'll draw perpendicular to any 3 tangents, so let's say this is F1, you know, if I'll draw perpendicular to that tangent is F2, and if I draw perpendicular to the 3rd tangent is F3. And now it's a well-known fact, just now I proved the foot of perpendicular will lie on tangent at vertex. So with respect to this triangle, PT1 S1, we have a special point S such that the foot of perpendicular is collinear. It means S must pass through the circumcircle of the triangle formed by PT1 and S. And what is S here in this case? Focus. And hence this property is proved that the circumcircle of the triangle form must pass through the focus. The other corollaries of the Simpson line and that property also tells you that the orthocenter of the triangle form will lie on directrix. So this also follows from one of the very basic theorem of Simpson line. Like if you reflect the point, okay, if you reflect the point, so the line joining point P and the orthocenter of the triangle will be bisected by the Simpson line. So we have S focus and we have some orthocenter H. So S and H will be bisected by this Simpson line, bisected by tangent at vertex. So this will be equal. It means focus must be somewhere on the directrix. I'm not claiming like it will be exactly on the x-axis, but it will be somewhere on the directrix so that it is bisected by Simpson line. So both these properties are proved. Now once you prove this property, all these results are obvious. So let me start with the fourth result first. So orthocenter of first triangle PT1S1. As you can clearly see, according to the diagram, we have P, T1 and S1. So orthocenter of this three triangle P, T1, S1 of triangle formed by P, T2 and S2, because both of these circumcircle will pass through focus, right? So their orthocenter will lie on directrix, which is x equals -1. So what is x1 plus x2? So x1 equals -1, x2 equals -1, which will give 2 as the answer. So we killed one of the problem. Next question is what is ST1 by ST2 and SS2 by ST2? Now we know since there is existence of a circle, so if we join ST1 and SS1, so there is a remarkable result that we are getting, because this is cyclic quadrilateral. So if I take this angle as θ1